think that's, you don't need to avoid this one.
Oh, is that the thing that you turned on?
Yeah.
Oh,
There's one other knob, but.
do it.
No, I did.
Okay.
That's
Experiment.
very uncomfortable for me. Okay, well, sorry, we had some audio issues, but I think we can hear you fine enough.
Okay.
We'll just play it.
Okay.
Yeah, today we're very happy to have Arpith Kumar. He's been here before for our school, I think 2 years ago, right? Okay.
Yes, almost 2 years. Yes, now.
Almost 2 years ago. Well, in any case, he's now doing a postdoc at the Central China Normal University. And the topic of his talk will be QCD in strong magnetic fields, conserved charges in the equation of state. So please start whenever you're ready.
Okay, thank you, Sam, for the introduction. So good afternoon, everyone. I suppose there is afternoon in Johannesburg at the moment. And before I begin, I would like to thank Anosh and Isabel for organizing this talk and giving me this wonderful opportunity to discuss my recent work. So I'll be talking about QCD in strong magnetic fields. And in particular, I'll be talking about how the strong magnetic fields, they modify the behavior of conserved charges and thermodynamic equation of state of QCD. So this is based on our 3 recent works with my collaborators at Central China Normal University. So let us start with a very broad perspective, like what is QCD is and what is the intuition behind the fundamental force in QCD, that is strong force. So QCD is quantum chromodynamics. So it is formally, it is a theory, it is a quantum theory of strong forces or strong interactions. And it is one of the 4 fundamental forces of nature. So the other ones like gravity and electromagnetic force are much more familiar to us. And so the origin, to understand the origin of the strong force or strong interactions, we'll need to ask questions like what forms hadrons and what keeps the nucleus together, bound together. So going back into the history, like for last 1 century, we know that atoms are made up of nucleus and which comprise of protons and neutrons. And this nucleus is surrounded by electrons, which are spread around the nucleus because of the electromagnetic force, where the like particles, charges repel each other, while the opposite charges, they attract. And because of this property, the electrons are spread around the nucleus. While if we zoom in and go into the shorter scales, that is within the nucleus itself, we'll find that if we apply the principles of electromagnetic force, it would have very strong, enormous repulsive forces. So then the question arises, what keeps the nucleus bound together? And that's where the intuitions behind the strong nuclear force came into existence, that there has to be some other force which is even stronger than the electromagnetic force, and it keeps the protons and neutrons bound together. So, however, this still doesn't define the origin of this strong force. And for that, we have to probe even inside the protons and neutrons. And somewhere in 1960s, somewhere in 1916, even smaller and more fundamental building block particles, quarks, were proposed. And this is a simplified picture where each proton consists of 3 quarks, which are confined due to strong force. And since everything here is happening at very shorter scales, so it has to be a quantum force. So that's why we have quantum chromodynamics. So it's a quantum force. And there are very strong analogies with the electrodynamic force, the quantum part of electrodynamic force, which is called the quantum electrodynamics. So the analogy is that instead of electrons, we have quarks here. And we know that electrically in QED, the electrically charged particles, they interact by shooting like photons back and forth at each other. And in quarks, in QCD, these electrons are replaced by quarks, and they interact by via gluons. And but there are certain differences between these theories. That is, the force holding the quarks, as we discussed, works very differently, and the relevant and the nature, the origin behind this differences between these forces lies between some subtle parts like the electric charge, the relevant charges. The relevant charge in QED is an electric charge which has two variants, like positive and negative charge, while in QCD we have three variants, and we have and it's called a color charge. And these red, green, and blue, they are just representative of these three different color charges. And so similar to photons, we have gluons here. However, as we can see that there is a line, this connection missing for protons with the electric charge, because photons themselves do not have any electric charge, while gluons, they carry the relevant charge of QCD, that is electric, that is the color charge. So this fundamental property has major consequences in how differently these two forces, which have strong analogy, they work. So what are these consequences? They can be reflected in some of the key properties of QCD. And so one of the key properties is confinement, where the color, where we have colorless bound states, color neutral bound states of, say, two quarks, which can be represented by this scheme, by this picture, where we have two people running in a park, and confinement is generated by them because they have a proper distance with each other, and they never go far. They never go far apart from each other, and we call that confinement among hadrons. And so this is confinement in QCD. And while if we get many people, such people together, like in a marathon, so there will be a situation where many people, there are many people surrounding each other, and it doesn't matter who your partner is. So at different point of time, you'll be running with different partners, so you can freely move around. And the idea is that the crowd screens the forces among your partner. So, so this is the fundamental behind the deconfinement property, and this results in the constituents of hadrons, that is the quarks and gluons, to not care about their neighbors, and they can freely move around. Yeah, so this is deconfinement, and it leads to the quark-gluon plasma. And so this situation we have definitely encountered in various physical systems, but we have seen this QCD phase diagram for different control parameters, temperature and chemical potential. And we can see that for if we go to higher temperatures and for a fixed chemical potential, we can again achieve deconfinement. And similarly, if for a fixed temperature, if we go to higher chemical potentials, that is more density, as we see in this marathon picture, again we can achieve deconfinement, that is the quark-gluon plasma phase. So what this QCD phase diagram depicts, let's try to understand this in more detail. So it actually depicts different physical systems from the, so on the left, we have this phase diagram again, like versus temperature versus chemical potential. So it depicts various different physical systems, starting from the early universe to neutron stars at very large chemical baryon chemical potentials. So what happens in the early universe is that in its evolution, which starts from so the early universe, it started from a very hot and dense medium, as we can see from the right figure here, and where the medium contains the degrees of freedoms as quarks and gluons. But eventually this medium, it cools down, or the density decreases, and at some point it is too cold or too loosely packed with the decrease in the density that you start forming hadrons. And that's when that's where what we see in the phase diagram also, that from the deconfined phase we enter the confined phase. And similar properties can be understood in neutrons and neutron-star mergers as well. So so how do we encounter these situations today? How do we study these properties of the early universe? And we do that by in heavy ion collisions, that is the experiments which require very large, big colliders, as they exist at RHIC, the relativistic heavy ion collision, and LHC. So RHIC at Brookhaven, US, and LHC at CERN, Switzerland. And what they do is they take two nuclei, suppose lead-lead nuclei, and they and these beam of these two nuclei, they run in opposite directions, like one beam goes in this direction and the other goes in the opposite direction, and they intersect at some point, like where they collide, and the constituent, and in this collision, the constituents of these nucleons, they interact strongly. They interact through quarks and gluons inside these nucleons, and it generates a very hot and dense medium similar to the early universe, which we discussed. And with expansion, this medium, the quark-gluon plasma, and with expansion, this medium cools down and the density decreases, and similar to the early universe, and we reach freezing point where we start to create some hadrons, like protons and neutrons. And so this picture is there on very large experimental colliders. So how do we study the similar physics on the theoretical side? So similar physics as heavy ion collisions and early universe on the theory side. So one promising way to do this is lattice computations. And so it's a first principles way of studying the strongly interacting matter theory. And this, so we have the same QCD phase diagram. So here I have introduced some lattice computations represented by this blue and this yellow bands. And what they represent is a pseudo-critical line. So so this was first this idea of the existence of the pseudo-critical line was first introduced by the lattice calculations. And the thing is, the concept is that this transition from deconfined to confined phase for early universe, or which we see in the heavy ion collisions also. Heavy ion collisions, now the data points are represented by this. So we have data points also by this red and purple data points from the heavy ion collision data. So the idea is that the deconfinement to confinement transition is it happens too quickly, but it's not an actual phase transition. So it's called a pseudo phase transition, and this temperature where this transition happens is called a pseudo critical temperature, which is around 155 MeV, and which is much larger or much hotter than the temperatures which we are used to, like even 5 orders hotter than the temperature of the sun. And it reduces, one of the key properties is slightly reduces as we keep on increasing the baryon chemical potential. So on the right, I show some pictures from a couple of pictures from the supercomputing facility at CCNU. It's called the NSC3 cluster. It's the Nuclear Science Computing Center, and it has hundreds of V100 and A100 GPUs, which are used to do similar lattice computations as shown in this phase diagram on the left. And so then the question arises, what exactly do we put on these computers to simulate? And so we on these computers, we try to study the thermodynamic matter properties, as we have seen in the deconfined and confinement phase diagram. And so we put on computer the theory of strongly interacting matter, and this theory is represented by this grand canonical partition function of QCD. And on the right-hand side of this equation is a path integral. So we have learned in 1960s, early 1960s we learned from Feynman that the theory of strong interaction can be formulated as a path integral over gluons and quark fields. And so I won't go into the mathematical details, but this the weight of this path integral is in the Euclidean space-time. It resembles the Boltzmann factor of the statistical mechanics, and the action, and it's this Boltzmann factor, the weight is given by the exponential of negative of the action, and the action itself is an integral over the time, the temporal component, and the volume, the thermodynamic volume, and it's an integral of the Lagrangian density, which describes the QCD, the gauge fields in the gauge fields, the field strength tensor F mu, and it also has the interactions of quarks with the gauge field, and which is given by this bilinear form here, bilinear form of fermions or quarks. And there are different flavors of quarks from UDS to top. And this theory for QCD, it has the colors degree of freedom to 3, set to 3. And so, but again, the problem with solving this equation is that the path integral itself is an infinite dimensional quantity, and so it poses problems in understanding the thermodynamics from theoretical side. So as a solution in 1970s, Kenneth G. Wilson explained how one can formulate and discretize this theory of QCD on a 4-dimensional space-time grid, as shown on the left, and with quarks on the lattice points and gluons as the links. So how do we exactly do this? Is we first integrate out since this is a bilinear form and the fermions have certain properties of Grassmann variables, so we can integrate out the fermion degrees of freedom. So as a good consequence, we have the integral only over the gauge fields. However, this gives us however, as a price, so the price we have to pay is that we have to compute these large fermion determinants in turn, and and this is what we compute, and this is the theory which we perform simulations for on these big supercomputers. So on the lattice side, we take periodic boundary conditions. So on the temporal side, we have so in all 4 directions we have closed periodic boundary conditions. In the temporal direction, it gives us a link to the temperature, while in the spatial direction it gives us the thermodynamic volume, and so which are represented by this n tau and n sigma. So suppose we can take a lattice with volume, the total volume as 32 cube times 8, where 32 cube would represent the thermodynamic volume, and 8 would represent the the temporal component temperature. And A here is the discretization constant, and it is also known as lattice spacing. So to get then finally to, sorry.
Can you hear me?
Yes, yes,
Hello?
I can hear you. Yes.
Sorry, this is Isabel. I just wanted
Hi,
to ask.
hi. Yeah.
Hi, and this periodic boundary condition, how important is it that it has to be a periodic boundary condition? So I think I understand if you're in the temporal direction, I think I believe that it has to be periodic, but in the spatial direction, do you lose any information if you use some other boundary condition, Dirichlet or something?
Yes. So yes, so boundary conditions are also are very important to maintain the exclusivity in these lattices. Like we can have different lattices as well, but I'm not sure whether we can have something very different, because there are certain boundary conditions like twisted boundary conditions one can impose to keep certain other symmetries intact. But I'm not sure whether the boundary conditions like Dirichlet boundary conditions would keep the symmetries of the theory, like the gauge symmetry, intact. So I think periodic boundary conditions are one of the commonly used to formulate such theories on lattices, which can incorporate all the fundamental symmetries which are there in the continuum theory. So it's about like how much symmetries we can preserve when we place theory on the lattice.
I see. Thank you.
Thank you for the question. So then the basic idea is, so we perform simulations on such lattices, and then to compute observables which can be considered as on physical scales. We need to take and we need to get closer and closer to the continuum theory. So we need to take the continuum and the thermodynamic limit, which is given by this the vanishing lattice spacing. Then also in this in the lattice QCD, we also have different discretization schemes, which I won't go into details, but there are various schemes like staggered Wilson and domain wall fermions, especially for fermions here, and which can all are again important to preserve the symmetries in the continuum theory, as well as to reduce the discretization errors. And also finally, there are no free parameters in lattice QCD simulations. So we fix, unlike the low energy effective field theories. So but we still have to fix certain quantities to get to the physical settings. So in our scale setting, we fix the quark masses on the lattice, and we fix them to get to the physical pion mass or the kaon masses. And so this results in us. So this is the scale setting which we use. So one of the most important bottlenecks of these simulations is that even though we have integrated out the Grassmann variables or the fermion degrees of freedom, so we have to compute this huge determinant or the trace of the matrix inverse, which is one of the bottlenecks in the simulations. So once we, so this is the a brief in a nutshell picture of the lattice QCD simulations. So, okay, so coming back to the phase diagram that we were discussing for three different, so where we have various different physical systems, especially early universe, heavy ion collisions, and neutron stars. So we usually discuss this with control parameters, temperature, and the chemical potential. However, all of these systems, almost all of these systems, they have magnetic fields. And so idea of this work or this program of works we have considered is to understand the phase structure, this QCD phase structure, with in presence of magnetic fields as well. So one of the advantage of studying the phase diagram in magnetic fields using lattice computations is that it doesn't pose any sign problem. So introduction of magnetic field doesn't lead to any sign problem. And the motivation is that the magnetic fields are present ubiquitously, so they are everywhere. But and even in the systems of interest, like in these major domains, there are strong magnetic fields. So I'll just come back to that in the next slide. So the idea is to study the interplay between the temperature and the magnetic fields effects, and also to benchmark for the imprints in heavy ion collisions. So heavy ion collisions also have strong magnetic fields, and if certain imprints are left in the final stages or the freeze out stages. So, yes, sorry, yes, please go ahead.
When you say that the magnetic field does not introduce a sign problem, so I'm not actually very familiar with these sign problems, but do you mean that the other sign problem still exists, it just doesn't introduce its own additional sign problem? So
Yeah.
otherwise I could just take these like other calculations and just add a magnetic field, yeah? That would solve the sign problem?
Yes, thanks for the question. I should have clarified this more clearly. Actually, so I will come back to this again once more, but so the idea is that with chemical potential, there is always a sign problem. So that's why we need to tailor expand in the chemical potential direction. And there are several other control parameters also, like electric field, and which will have similar sign problem, which is because of the complexity in the action and how these control parameters enter the QCD, so how these control parameters enter the QCD action here. So the chemical potential actually enters into the temporal component of the action. So it leads to a sign problem, and especially it leads to a complex action problem. So sign problem in Monte Carlo, complex action problem in general. And while the magnetic fields, they come as, I will discuss this again. So they come as a curl of the vector potential. So they come in the spatial component. So it doesn't introduce any sign problem, or it doesn't have any issues with the gamma 5 hermeticity, which is essential for keeping the action real. And so that's why, like, because it comes in the spatial components, it doesn't introduce any sign problem itself. But there will be sign problem for if you try to study the in general T mu EB sort of QCD phase diagram. So that sign problem would be from chemical potential. Yeah, thank you. So as we were discussing that these magnetic fields are actually ubiquitous in nature. On Earth's surface, we see that they are about 0.6 Gauss, and in the core, it can go up as high as to 25 Gauss. Common and handheld magnet can have 100 Gauss, and the magnets which we have created, man-made magnets on Earth, they can go up to 10 to the power 5 Gauss, while the systems we were discussing, the three major cornerstone domains of the modern physics, they have strong magnetic fields. And what they mean, strong magnetic field means is that the orders of these, the strength of these magnetic field is comparable to the characteristic scales of interactions in these systems. So in early universe, we have these primordial magnetic fields coming from the initial density perturbations. And also in the neutron stars, this is a schematic of the nearest neutron magnet stars we have, like, which has the strong magnetic fields. And so they are, so even in neutron stars, they are relevant. And even in heavy ion collisions at the initial stages, they are produced. So so study of QCD in magnetic fields is highly relevant for the QCD phase diagram, because they are there present, and they can affect the they can non-perturbatively affect the QCD phase diagram. So so my focus initially would be on the heavy ion collisions. So again, they have orders comparable to the intrinsic scale of interaction, that is in the initial heavy ion collisions, where the spectator particles, they move at very high velocities, and generate strong magnetic fields. They can go up to the order of the characteristic scale of QCD, lambda QCD. And and the initial strength of these magnetic fields have been studied to be around, by some certain model dependencies, to be they can get as high as 70 mpI square at LHC and 5 mpI square at RIC. So the caveat, although, is that these magnetic fields are expected to decay very fast. So that means that with the collision, as the collision happens afterwards, their strengths will reduce drastically. And but there have been certain model dependencies which have been studied. So for vacuum, they decay very fast. But if we introduce certain mediums, so the in-medium properties can sustain the lifetime of these magnetic fields. And then the question arises whether whether the magnetic imprints, they exist in the final stages or the freeze-out stages of the heavy ion collisions, and can we measure them? Can we study them from heavy ion collision freeze-out conditions? So this hunt has led to various, on the theory side, it has led to various complementary studies from low energy effective field theories and first principle lattice QCD. So magnetic fields, they don't introduce any sign problems. So there have been a lot of interest in the past decade. And we have now established some now well-known phenomena such as inverse magnetic catalysis and catalysis, how it changes the property, how magnetic field changes the properties of the of QCD and thermodynamics. So I won't be going to details of magnetic catalysis, but as we saw for the temperature, the pseudocritical temperature lowering with chemical potential, here also with magnetic field, we also observe certain similar effects like lowering of pseudocritical temperature as we increase the strength of magnetic field. So however, all of these studies have been based on chiral condensates, which is an order parameter for this confinement deconfinement transition study, but they are not accessible in heavy ion collision experiments. So you cannot compare between, so even with this vast knowledge of thermodynamic modifications from magnetic field, we cannot compare exactly with the heavy ion collisions. And that's where the fluctuations of conserved charges comes in. So as we were discussing at finite chemical potential, the Monte Carlo path integral Monte Carlo encounters this infamous sign problem because the action becomes complex. And so we circumvent this for chemical potential, finite chemical potential, using Taylor expansion. So what we do in Taylor expansion is we Taylor expand the grand canonical partition function, which depicts the thermodynamic pressure of the system in terms of chemical potentials. So suppose we Taylor expand this in conserved charge chemical potential. So these conserved charges are represented by this BQS, that is baryon is, B is the baryon number, Q is the electric charge, and S is the strangeness. And they are the conserved charges of strongly interacting matter. So in this Taylor expansion, the coefficients of this Taylor expansion are nothing but the fluctuations and correlation among conserved charges, this chi BQS. So one important note is that since in QCD we start with the flavor degrees of freedom or the quark degrees of freedom, so we will definitely first study, so what we get is the correlations among these quarks, not the conserved charges, but using these properties of quarks and what conserved charges they carry and these chemical potentials, we can always go back and forth, and from there we can compute the fluctuations and correlations among conserved charges as well. And the advantage of doing this is that they are not only computable on lattice, as we mentioned, they are also experimentally measurable. How they are experimentally measurable is by these fluctuations in heavy ion collisions of net conserved charge distributions in this particular manner. So they are connected to these conserved charge fluctuations. They are connected to the cumulants on the on the in the heavy ion collisions. So, so let us begin with brief details about the lattice. So I'll quickly go through this. So as we were discussing about, so we we discretize a 2+1 flavor theory. So we consider 2+1 flavors. So 2 means like we have degenerate U and D quarks and 1 for strange. And we place it on a lattice, and we have certain improved actions as we were discussing for discretization and symmetry preservation. And we have physical pion mass, that is the scale setting is done such that we are there with the physical settings of the world. And we perform these simulations on 2 lattices. So our aspect ratio, temporal and so the temporal and the spatial volume are such that we have these 2 lattices, and we perform continuum limit. We take the continuum limit as continuum estimates. So the idea about estimate is very technical. So it's not a direct extrapolation. So extrapolation would require minimum 3 lattice spacing. So these are just continuum estimates. However, we have established consistency between these estimates and extrapolations for the observables which are in interest, the thermodynamics susceptibilities and these fluctuations of conserved charges. So, and in the control parameter space, like we were discussing the temperature, chemical potential, and magnetic field. So temperature is focused around the transition temperature of QCD, that is from 145 to 166, focused around 155, because it will reduce with magnetic fields. And at the heart of this work is strong magnetic fields, which, as we were discussing earlier, they come as a curl of the vector potential. So there is a gauge invariance associated with this. So we fix the gauge with Landau gauge, which results in uniform magnetic fields in Z direction. And there are certain more technical details about the introduction of magnetic fields. So first is, so I'll briefly go through them. So the periodic boundary conditions on this lattice, along with the Stokes theorem, they demand that these magnetic fields would be quantized. So instead of continuous spectra of magnetic fields, we'll have discrete values which are controlled by this, this flux NB. And in our simulations, we consider NB up to 32, from 1 to 32. And this gives us very strong magnetic fields going up to 0.8 GeV square. So these are much more larger than what we can expect in heavy ion collisions. So in heavy ion collisions, we'll restrict ourselves to 8 MPi square, which might be a good estimate. So we run these simulations on the in-house NSC3 cluster we discussed, and we first compute these susceptibilities or these fluctuations and conserved charges, fluctuations and correlations among conserved charges, chi-BQS. And we can also consider, later on, we will also discuss how we can obtain certain bulk thermodynamic properties like pressure, entropy, and energy density. So let us first start with these fluctuations and conserved and correlations of conserved charges. So, so from the naive interplay between electric charge and magnetic field, one might expect that it is the electric charge fluctuation which should be heavily affected by the magnetic fields. So on the left, we plot the electric charge fluctuation as a function of magnetic field strength, EB in GeV square, and our continuum estimates, as we discussed. So n-tau 8 and n-tau 12 data is given by these data points in blue and red, but the continuum estimate is a band, this golden band, and it implies that there is no sensitivity of these electric charge fluctuations to magnetic fields, and up to 8 MPi square, up to 0.14 GeV square. And so this is surprising because one might expect that there should be a good sensitivity with respect to magnetic fields. so since this is at a temperature 145 MeV, which is well below the pseudocritical temperature, like at least for vanishing magnetic fields, it's around 155 MeV. So this is well below. So we are still in the confined region, as we were discussing, and there we have hadron gas, hadrons like protons, neutrons, and a gas model of them. So we study this gas model in presence of magnetic fields. So it will have certain spin associated with the magnetic field direction. It will have certain Landau levels, L from 0 to infinity. So, but the lowest Landau level will have the most contributions. And there will be some Taylor expansion coefficients, which are not that important. So the important thing is that we consider this pressure for various different hadrons and individual contributions from hadrons. And we try to study like why there is no sensitivity to magnetic fields. And so one important property I should definitely mention is that introduction of magnetic fields, it quantizes the transverse momentum. So we only have so from the 3 space momentum, we only have the momentum in the direction of the magnetic field, the longitudinal momentum. Say magnetic field here we consider in the y direction. So only the longitudinal, the y direction momentum will survive. The xz direction momentum will be quantized, and this quantization is given in this manner, that the energy is, the dispersion relation is highly modified by this quantization. So what we see from HRG, so coming back to the picture, the plot, is that the dominant contributions come from pions, and these the contributions from pions decrease with magnetic fields. There are some increase with for heavier pions like kaons and rho mesons. So, but overall there is no sensitivity at all, even from the dominant contributions from HRG. So from these mesons pictures, electric charge, meson-dominated electric charge pictures, charged meson-dominated. So let us go to the charged baryon-dominated picture, that is the BQ correlation at the same temperature. And here we see that the charged baryons, they have strong sensitivity. The baryon-electric charge correlation, BQ correlation, it shows high sensitivity with magnetic field, and it enhances by a factor of 2.4 at 8 MPi square. And so as we can see from the continuum estimates, and similarly to understand the behavior from the hadron resonance gas model, because this is still at a low temperature. So we see that the dominant contributions, they come from protons at vanishing magnetic fields. However, there is a crossing between the delta plus 1232 contribution with magnetic field, which starts to dominate later. And one crucial part here is that if we compare the delta plus nature, the nature of the delta plus resonance and the continuum estimate, it appears that most of the dominant contributions come from the delta plus baryons. So, so the most of the EB dependence is coming from the delta plus baryons, not from protons, not from higher mass or delta plus baryons. It comes from the delta plus 1232 baryons. So, however, then there is again an issue that these delta plus 1232 baryons, they are not experimentally measurable. Why? Because they decay very fast. They undergo strong decays to protons and pions. So one cannot directly measure them in experiments. So, but we can account them from decays, like from their decay products. We can definitely consider how the contributions should be, considering this particular decay equation. So interestingly, this decay equation is almost 100%, like 100% branching ratio to protons and pions, charged pions. So then to understand this, we consider some HRG proxies, so which can be measured in experiments as well. So to consider these delta plus like baryon resonances. So there will be some memories carried from these delta plus decays to protons and pions. So here we consider the ratio, RCP-like ratio of chi-BQ correlation. So that is like we take a ratio with the vanishing magnetic field. So now from the T equal to 145, we have come to TPC. So we are along the freeze-out line or the pseudo-critical line. And so we have measured the pseudo-critical line along the magnetic field, how the temperature changes, and we are varying according to that. And we have taken a ratio along with, we have taken normalized it with vanishing magnetic field case. And we see that this particular observable ratio observable has an enhancement of 2.1, which is again agreeable to 2.4 enhancement. And this is the particular part which establishes that, because since it's along the freeze out line, that BQ correlation should be a QCD magnetometer. It should be a magnetometer of QCD. It can detect the magnetic field induced enhancements in QCD. And to measure this properly from experiments, exclusively from experiments, we introduce proxies. So instead of this ratio BQ, we consider the sigma 11 QPID proton ratio. So what is proxy? What it means is that instead of the baryon, net baryon, which we were considering for the correlation, we now consider the decays of the resonance to protons. So instead of net baryons, we only consider the decay product, that is the proton for baryons. So all the baryons are decaying to protons. And similarly, for the electric charge, we consider all the decays to pions, kaons, and protons. So in general, our proxy is that instead of these BQS, the baryon, electric charge, and strangeness charges, we only consider protons, pions, and kaons. And instead of these quantum numbers as BQ, we consider the weights coming from all the decays of all the resonances to protons, pions, and kaons in this manner. And we see that represented by this magenta line, that even the proxies are very much closer to the full HRG, and also the EB dependence is very well captured closely to the continuum estimates from the lattice as well. So this is highly promising, and so that's why we consider some observables which are similar to those considered in experiments, in heavy ion collision experiments. So we consider a double ratio observable. So heavy ion collision experiments, they usually consider double ratios to suppress volume dependencies. So in the numerator, we fix the magnetometer, that is BQ correlation, and we consider several different appropriate observables in the denominator. So first observable we consider is the electric charge fluctuation. Why? Because we already observed that it doesn't have any sensitivity to magnetic fields. So it should work like a perfect in the denominator, and the enhancement should be there. So we proposed this, and we see that there is a good enhancement of 2, a factor of 2 from magnetic fields as we increase the magnetic fields up to 8 ampere square. And okay, so 8 ampere square. And so similarly, we also introduce certain cuts in the experiment. So these experiments, they come up with certain detector acceptance cuts, and we see that they are also showing some sensitivity to magnetic fields. And then Alice collaboration also recently measured similar observable, and they saw that for certain detector acceptances, as given in set 1, they obtain around 25% for similar observables, 25% enhancement with magnetic field. So so here what it means is that with centrality increases, these magnetic fields are expected to increase in the heavy ion collisions, because these magnetic fields are generated by the spectator particles, which are away from the center of the collision. So they are expected to be more in the peripheral parts of the collision rather than the central part of the collision. And in set 2, in detector, the new data from Alice, they measure about 60% enhancements in the data, which is keep on increasing, and it is getting much more closer to the continuum estimates which we proposed, and also is much more closer to this magenta line here of the proxies which we have suggested. And we also suggest one more observable, that is the ratio with QS, the electric charge and strangeness correlation, which shows high sensitivity from our continuum estimates like 2.2, and the proxy also shows 1.6 to 1.75. And the ratio of the proxies to lattice QCD data is about like almost 75% to 85% of the sensitivity is retained. So it would be a highly effective probe, even more effective probe than the electric charge ratio, which we took earlier. So this is what we are currently suggesting for the measurements, but and these measurements are still ongoing at LS. So, so with these magnetometer discussions relevant to heavy ion collisions, so we can move to the next part. So I'll quickly go through this, and so this is like we can consider, we can construct using the fluctuations of conserved charges. We can construct certain thermodynamic observables or the equation of state. So what is equation of state is that it is a description of the equilibrium properties of a strongly interacting matter. So how do we do that? So for that we study like thermodynamic observables like pressure, energy, and entropy density as functions of control parameters. And again, since magnetic fields, we discussed that magnetic fields are strong magnetic fields are there in these three cornerstone domains of modern physics, and they affect the equation of state as well. So, and these equation of state effects on equation of state will indirectly affect the evolution properties of these three domains, like the Friedman, like the energy scale factor evolution given by the Friedman equation, the mass radii relations given by the TOV equations, as well as the hydrodynamics evolution in the heavy ion collision. And all of them, they need the equation of state to solve these equations. So the effects of magnetic fields on equation of state are highly relevant to study. And so using these fluctuation of charges, we try to construct the equation of state, like the pressure up to leading order. It can be, as we saw in the Taylor expansion, it is an expansion with chemical potentials, and we can fix this up to leading order contribution with factors of with orders of 2. And in this scenario, we'll again be concentrating on the pseudocritical temperature, near the pseudocritical temperature, but our magnetic field strength will go up to as strong as 0.8 GeV square in this theoretical study. So the leading order pressure is given by this by this particular form, where we have the baryon-electric charge fluctuations relevant to the baryon chemical potential. And we have certain other chemical potentials like electric charge and strangeness. And if we want to measure the response of this coefficients, the leading order coefficient of pressure up to second order coefficient of pressure, we would have to like fix the other chemical potentials, because there are so many control parameters still, mainly the 3 chemical potentials. And these chemical potentials are actually related to each other. And how do we do that? We use the strangeness neutral conditions, which are again relevant to the initial nuclei, or the freeze out, also the freeze out conditions of the heavy ion collisions. So one, I'll just mention quickly, one simplified way to get rid of these terms is like just take the vanishing chemical potential term. In that, the only contributions will be from the baryon electric charge fluctuations. So this is a very simplified way. But for relevant to heavy ion collisions, and initial nuclei condition is the strangeness neutrality. So which means that there is no strangeness density at the start of in the initial nuclei condition. So we fix that to 0. And the other is that the expect ratio, the ratio of the electric charge to baryon is also fixed, and it is known as the isospin parameter or the isospin symmetry. So suppose we have lead-lead collision system. So directly seeing from the protons and neutrons, we can say that what is the electric charge to baryon ratio, and it is around 0.5, like it is exactly around 0.4. So that's what we will consider. And how do we implement these constraints, these strangeness neutrality constraint? We again Taylor expand the chemical potentials in terms of baryon chemical potential. And we can get some leading order of this Taylor expansion, which is nothing but this ratio over the fluctuations of conserved charges, and with some isospin parameter R here. And we have for electric charge as well as for strangeness, Q1 and S1. So, sorry, yeah, please go ahead.
About 5 more minutes.
Okay, 5 more minutes. Okay, so thanks. Okay, so I'll quickly mention some of the properties. So before going on to the pressure, the relations of the proper modifications on pressure coefficient, I'll quickly mention the modifications on these Q1 and S1. So so we plot this Q1 with a negative signature versus magnetic field, and we see that at R equal to 0.4 condition, which is relevant to lead-lead collisions, we see that the signature of Q1 is negative. So we have plotted it with a negative sign. And why is that? It's because, again, because of the isospin symmetry, that in the lead-lead nuclei, we have less number of protons than neutrons, which will imply that the electric charge chemical potential would be negative. Then in the weak regime of this, we can, so on the left, actually, we plot Q1 as a function of magnetic field for 3 different temperatures around the pseudocritical temperature, like 145, 155, and 165 for the strangeness neutrality conditions. They are represented by this these bands. And for the weak EV regime, like up to 0.14, that is 8 m-pi square, we can get some intuitions from HRG, similar way we did earlier. And we see that there is an enhanced degeneracy, like as we were discussing, the phase space, the momentum space is quantized in the transverse direction. So we only have the longitudinal direction left. And so once that is quantized, its degeneracy in the transverse momentum is also increasing, like the lowest Landau level would be highly populated because of this. And also for certain cases like delta plus baryon, the energy of the lowest Landau level will also be lowered. So all of them will make the charged, the density of the charged protons, like charged baryons, go up. However, we have this constraint that R equal to 0.4. So it should be maintained. And to maintain this, the Q1 goes even more negative. So that's why the Q1 is getting more and more negative. So one last property of Q1 is that in the strong EV regime, so the EV which we have considered, there we see saturation of Q1. So it is not going to go beyond, increasing beyond this. And why this happens? So again, like we consider the HRG model for low temperatures and low chemical potentials. So we can consider the ideal gas model for the quark gluon plasma, where the flavors would be quark flavors. And we can take some intuitions from there. And we see that the lowest Landau level here has a linear dependence on magnetic field. And so suppose the lowest Landau level gets more and more dominant. And since this is a ratio observable, so it will get canceled out. So that's why we have a saturation here. So similarly, we can, and the most important part is that there are crossings among temperature bands. These temperature bands, they have crossings. So there is a change in the hierarchy. So lowest temperature was having lowest contributions, but now it has highest contributions. So, and this reflects in the non-monotonic temperature dependence. So the slope changes. So I will quickly go to the pressure now. So just discuss these crossings in respect to the leading order pressure contribution. So, we come here on the, we came across this pressure leading order pressure contributions, and using strangeness neutrality, we can introduce Q1 and S1 from the chemical potentials, electric charge and representative of electric charge and strangeness chemical potentials relevant to strangeness neutral systems. So, and we see that the pressure coefficient again plotted in the similar manner for 3 different temperatures versus magnetic field. It keeps on increasing, and this can be explained by HRG. like why the pressure will keep on increasing because of the degeneracy increasing. But the most interesting part is that at higher pressure, higher magnetic fields, we see crossings among these temperature bands. And this actually reflects to the non-monotonicity in the temperature dependence. So at vanishing magnetic fields, we see that the pressure smoothly increases with temperature. However, as we keep on increasing the magnetic field, so this pressure starts to develop certain non-monotonic structures, and eventually there is a peak structure at the strong magnetic field. And this peak structure, or the inflection points here, they shift towards the left. So what this means is that it's a similar to TPC lowering effect as we saw for chemical potential, even in the magnetic fields. And so this is a highlight. This picture actually highlights the non-trivial interplay between the temperature, where the magnetic, where the pressure contribution increases with temperature because of thermal agitations, and near the pseudocritical transition. So it's mainly due to thermal agitations, and while a peak structure coming up because of the magnetic effects, non-trivial magnetic effects. So there are certain higher thermodynamic quantities like trace anomaly and energy density, which also reflect these the behavior because of these peak structures. So I will skip them. So quickly I'll go to the take-home messages. So first was that chi-BQ correlation is it acts as a QCD magnetometer. It's highly sensitive to detect enhancements due to magnetic fields, and it can be probed it can help to probe magnetic field imprints in heavy ion collisions. And in the equation of state, so one property which is most important or crucial is that in temperature bands we saw crossings, which results in non-monotonic structures in pressure growth, which highlights the non-trivial modifications, a non-trivial interplay between thermal and magnetic effects. So with this, I thank you all for your time and attention. Thank you.
Questions? Thanks for the talk.
Yeah, thank you.
So how big are your cyclotron orbits compared to your lattice size?
Sorry, which slide? Sorry.
So no, I mean just in general, these simulations. How big are your cyclotron orbits of charged particles compared to your lattice size?
So so the question, I suppose, is sorry.
The question is,
Sorry, my internet is slightly weak. Just okay. So the question is about the lattice size, right? Like, sorry, can you please repeat again? Like how? So the particles. Yes, please.
Is the lattice big enough for your charged particles to form cyclotron orbits?
So is the lattice big enough for the charged particles?
Make cyclotron orbits.
So
you're asking if, I think Isaac is asking, but correct me if I'm wrong, if the lattice is big enough to simulate a real lead-to-lead collision.
No.
Oh, sorry.
No.
Okay. I somewhat understand now. Like I think so. This would date back to here. So suppose we consider these lattice discretizations. So they come up with certain regularizations, like there will be an infrared regularization which will be controlled by this this lattice parameters. So I suppose the question is like, so whether these IR and these UV regularizations coming from the discretization of the lattices, is it relevant for the certain mass particles which we are considering? So yes, so I think I'm not exactly sure, like so we do see so from here, so we do see that the delta plus plus up to a certain mass, like this is already very like massive particle itself. So we see that the trends for delta plus plus are well, the EB dependence is well obtained by the lattice results, but I'm not sure about whether it would be large enough or the lattice spacing will be small enough for even large, even massive particles. So that I think I'm not sure about. Like we need to exactly like measure, compare the lattice spacing and check whether the UV cuts on that are comparable to the mass which we are considering. Yes, I think that this is very important question. Yes, thank you so much for this.
Arpith, I have a question.
Yes, please. Yes. Okay.
So, what is the typical size of this these lattices in physical units, in Fermi units? How big are they?
So, so in Fermi units, so I suppose I don't exactly know. Like I think I don't exactly know like how we can compare in that sense. So in Fermi units, I don't remember exactly. Like it should be 0.3 something. It depends on the lattice spacing as well. Like for these two different lattices, it should have, but it is comparable to Fermi. Yes. But I'm not exactly sure how much is the value of the A here, like the lattice spacing here in terms of Fermi units. Yes.
Okay, any other questions?
If you don't know the answer, that's also fine. On slide 12, you had you made a statement. If you could go back to slide 12, I forget now exactly.
Okay, yeah. Here?
Yeah, here, this plot on the right-hand side, where you said that you can compute this. There are these different models in which you have different kinds of media. But
yeah.
I was just curious if you are able to say anything about this or physics of these different models, because they're computing things before the thermalization time, right? For about like half Fermi. So, and there's a lot of stuff going on there. So what kinds of models are these? Because it's some far from equilibrium type of time, right?
Yes. So so I think this is also a very important question because it is at the heart of it, like whether these magnetic fields, they remain strong enough to cause some imprints at the relevant stages. So definitely these magnetic fields will not exist in the freeze out during, or they will be relatively smaller during the freeze out. So, but these different models, what they suggest is that the in medium properties like paramagnetism or so these properties of the medium itself, it can sustain these magnetic fields long enough so that they can leave certain imprints, like they can modify the contents of the constituents of the collisions in that way that the imprints of those modifications, like on the conserved charge cumulants, like these conserved charges, baryon and electric charge conserved charges, can be obtained later. So I'm not exactly sure like what goes into these models, specific terms like vacuum or eco or static quark, and how they compute exactly, like how the strength of the magnetic field from the initial the collision it will decay. So that I'm not sure like how these models are working, but it's about like whether the in medium properties are able to sustain these magnetic fields just long enough. And if they do, like so our idea of this work is, so if they do, then up to what magnetic field strengths, like here. So for what magnetic field strength do we see there is a modification in these cumulants or these fluctuations and correlations among conserved charges at fixed magnetic field strength, like which would be more relevant, and how big of a strength would be relevant to the changes in the experimental value. So I think this is also a very important question. I am not familiar with these model estimate calculations.
Okay, thank you.
Thank you. Yeah, thank you for the question.
Okay, I think that's it. So again, Arpith, thanks a lot for making the time and giving the seminar. And we hope to see you sometime here in South Africa.
Thank you. Thank you so much for this opportunity to discuss the work. Thank you so much.
Hi, Arpith, can you?
Hello, hi. Hi. Yes, I can hear you. Hi.
Okay, so I will talk to you later. Huh?
Okay, okay. Yeah. Thank you. Yeah.
Okay, thanks, Arpith.
Thank you.
Thanks
Thank
a
you.
lot. See you.
Thank you.
Bye.
See you.
Bye.
Bye-bye.